In this final video, we are going to prove the fundamental theorem of calculus, why it is true mathematically. And to do that, let's first remind ourselves what the definite integral is, right? It's the standard part of this Riemann sum. We're also going to need to remind ourselves of a couple of theorems that we showed in the previous videos, the rectangle property, the additive property, and the continuity of the integral function. We need all three of these in order to prove the fundamental theorem of calculus. So let's first start with part one that says if I've got an integral function, then its derivative is simply the integrand. So let's come down here, and we know that, so we're defining f of x to be the integral from a to x f of t dt. And we want to show that f prime of x is just little f of x. Right? That's what we want to show. That's what the first part really says. And so let's remind ourselves what a derivative is by definition. So if, say, delta x is an infinitesimal, then f prime of x is the standard part of the difference quotient. The change in y, so change in f of x plus delta x minus f of x, that's our change in y, divided by the change in x, which is delta x. It's probably been a while, you may have forgotten, but this is a good place to remind yourself since final exams are only a few weeks away. So that's by definition what the derivative is. And somehow we need to work with this object and show that what gets left behind is little f of x. So let's start evaluating. So we know what big F is. So this is equal to the standard part, and I'm going to slide the fraction 1 over delta x out here, times the difference of f of x plus delta x. So that's the integral from a to x plus delta x, f of t dt, plus the integral from a to x, f of t dt. And so I'm just putting in the definition of big F. So that's what that is, and then I can kind of rearrange things here, right? Because this is a to x plus delta x. And so this is equal to, using the additive property, this is equal to the standard part of 1 over delta x times the whole quantity. So I'm going to go from a to x. Sorry, I just caught an error. I put an addition here when it should be a minus. I was kind of looking at this and saying something doesn't make sense. So let's erase that and put what it should be as a minus. So this should be a minus sign. Sorry about that error, but we've caught it. So I'm subtracting here, right? F of x plus delta x minus f of x. So again, using the additive property, I'm going to break this up. This is equal to the integral from a to x f of t dt plus the integral from x to x plus delta x f of t dt, then minus this guy, minus the integral from a to x f of t dt. Again, all I did was use the additive property that says, look, if I've got an integral from a to b, I can break it up from a to c and c to b. And that's exactly what we did here, right? This is a to x plus delta x. Well, then I can just go from a to x and then x to x plus delta x. And that was a nice move because now I've got a to x f of t dt here, and I'm subtracting it here. So what gets left behind, right, these guys will cancel. And so this is just equal to the standard part of 1 over delta x, the integral from x to x plus delta x, f of t dt. Now let's put this on hold for a second. So I'm just going to put a place marker there and talk about this integral. So we know that little f is continuous on the whole interval. So in particular, we know that f, little f, is continuous on the interval x to x plus delta x. And since it's a closed interval, it's continuous. We know by the extreme value theorem that it has a maximum and a minimum. Let's say little m is the min of f on this interval and occurs when x is equal to c1, right? So f of c1 is the min. Also, let's say m is the max of f and occurs at x equals c2, right? So f of c2 is equal to big M. Okay, so what can we tell ourselves about these things? Well, first of all, c1 and c2 are in this interval, right? So c1 and c2 are in the interval, this infinitesimal interval, x to x plus delta x, right? This is an infinitesimally small interval because delta x is an infinitesimal. Well, if this is an infinitesimal interval, this means that c1 is infinitely close to x, and c2 is also infinitely close to x. And then since f is continuous, this tells us that f of x is infinitely close to f of c1, which is equal to little m, and f of x is infinitely close to f of c2, which is big M. All right. Why is that useful? Well, by the rectangular property, we know that any integral from a to b is bound above by the max times the length of the interval and bound below by the min times the length of the interval. So from that, we can use that the integral from x to x plus delta x of f of t dt is less than or equal to big M times the length of this interval, which is delta x. It's also bigger than or equal to little m times that interval. And so m is less than or equal to 1 over delta x times the integral from x to x plus delta x f of t dt, and that's no bigger than the max m. But remember what we just showed, that f of x is infinitely close to f of x, but the little one is also infinitely close to the value of f of x. And so then taking standard parts of everything, we have that the standard part, so f of x, which is a real number, is infinitely close or is equal to the standard part of little m, which is less than or equal to the standard part of that integral 1 over delta x, integral x to x plus delta x f of t dt. And that whole thing is less than or equal to the standard part of big M, which again, because they're infinitely close, must be equal to f of x. Well, now I've got that the standard part of this integral, the standard part is bigger than or equal to f of x and smaller than or equal to f of x. And so by default, this means that this tells us that f of x is equal to the standard part of 1 over delta x integral x to x plus delta x f of t dt. And coming up here, that's exactly what our star was, right? So that's equal to our star, which, again, kind of following back to our star, let's follow that up, right? Our star was equal to the standard part of 1 over delta x integral x to x plus delta x f of t dt, but that was equal to, lo and behold, f prime. And so now we've arrived that f of x is equal to f prime, which is our derivative with respect to x of the integral from a to x f of t dt. So that's the proof of the first part. And so then the second part of the fundamental theorem says, okay, what if we have an antiderivative? So the first part just says, hey, look, this integral function always is an antiderivative. But let's say we have an antiderivative we discovered some other way, kind of in the methods we've done in the previous examples. Then the definite integral is equal to the evaluation of the antiderivative between the endpoints. So how might we go about proving that? Well, let's say that f of x isn't our integral function now. Just say it's any is an antiderivative of f of x. Right, so what do we know? That f prime of x is equal to little f of x. Right, so we've got an antiderivative. And so we want to show that the evaluation between the endpoints of this function is the integral. So what we do is I say, okay, let's take the derivative with respect to x of the difference of f of x and that integral function, a to x f of t dt. Right, so let's take that derivative. Well, this is equal to f prime, because it's an antiderivative of f, is f of x. So this is equal, so the derivative of this function is f of x. And then by the fundamental theorem of calculus part 1, what we just proved, that the derivative of this guy is also f of x. And so the derivative of the difference of these functions is 0. And as we talked about in the previous chapter, that if I've got any function whose derivative is 0, then the function itself must be a constant. That's the only way for continuous functions. If I take their derivative and I get 0, the only way is if that function is a constant. So this tells us that f of x minus the integral from a to x f of t dt is some constant. If it's a constant, then it tells me that f of x is equal to the integral from a to x f of t dt plus some constant. Okay, so any antiderivative I get, so I don't care how you found it, it's going to be equal to the integral function plus a constant. That's what we just derived here. Well, that's not what we want to prove. We want to prove something about the integral, the definite integral. Well, let's use this fact. So let's look at the difference of f of b minus f of a? Well, by definition, here's what f of x is. So this is equal to the integral from a to b f of t dt plus a constant. That's what f of b is, minus the integral from a to a f of t dt plus that same constant. Well, the integral from a to a, as we've defined, is 0. So then that means that f of b minus f of a is equal to the integral from a to b f of t dt plus that constant, but then minus that constant as well. So these guys cancel out, and we just get what we wanted to prove. The integral from a to b of f of t dt is equal to f of b minus f of a, where big F is any antiderivative of f. So that proves the fundamental theorem of calculus, so we know exactly how to evaluate definite integrals, provided we can find an antiderivative. We always have an antiderivative, namely this function, the integral from a to x of f of t dt. That's always an antiderivative, but this function is not going to help us very much to evaluate the integral because it has the integral in its definition. So the next section will spend quite a bit of time developing rules on, given a function, how can you find its antiderivative? All right, so that wraps up section 4.2. Happy mathing to you, and catch you next time.